Light is an electromagnetic phenomenon, and you may already know that it behaves like a wave. It has an oscillating character because it has different frequencies. This is why in this session we will discuss the origin of the description of these waves, that is, the wave equation. To do that, we have a set of issues in this session. We start with the Maxwell equations. We then derive from that the inhomogeneous wave equation. And then we look at light waves at interfaces as an example. And after that, we will continue with some special cases, the wave equation in vacuum, spherical waves, plane waves. And in the outlook, we discuss how we can use these descriptions for applications, especially, of course, in laser technology. To begin with the deviation of wave equations, we start at the origin where all wave equations come from, that is the electromagnetic nature and structure of matter, and the behavior of this matter in the electromagnetic sense is described by the Maxwell equations you see here. So based on the Maxwell equations, we are now in the position to derive the inhomogeneous wave equation. To do so, we take one of Maxwell's equations, the one combining the curl of the electric field with the time dependence of the magnetic induction B, and we again apply the curl to this equation. Now we assume that we have no magnetization, so m equals 0, so that the magnetic induction gets directly proportional to the magnetic field. And the reason why we can do so is very simple, because at the frequencies we consider, which are of the order in light of maybe 10 to the 14, 10 to the 15 hertz, the magnetic dipoles in matter are too inert to follow these high frequencies, so there is no effect of the magnetic field. And in this context, then the equation simplifies to this expression here, just combining now the time derivative of the magnetic field with the curl of the electric field. So in order to further simplify, we now can use a second Maxwell equation, the one combining the time derivative of the dielectric displacement with the current density of free moving charges in space and time, which are related to the magnetic field with this second Maxwell equation. And then applying the relation of the polarization and the dielectric displacement d, we obtain an expression which we can simplify to this final expression of the inhomogeneous wave equation. So this is a pretty complex expression. That's why we should discuss it for a moment. What it reads is that the Laplacian of the electric field is correlated to the second derivative of the electric field to the time. And further ingredients in this equation are the change of the current density, J, so that is free moving charges, and the second derivative of the polarization with respect to the time, which represents the displacement of charges in the matter due to the presence of the electric field. So this is a pretty complex equation, but it shows us the relation and the combination of an external electromagnetic field with a matter, and in this electromagnetic nature of the matter we have charges leading to polarization, and we have maybe explicitly free charges moving. So this combination of matter and the free electromagnetic field is described in this general inhomogeneous wave equation. In order to make that a little simpler in understanding, we generated a little movie on a special case. To understand the meaning of this rather complex equation, we simplify it for a simple case. And the simple case is that we just take a moving electron, oscillating, which will generate an electric field, as we know phenomenologically. And this oscillating electromagnetic disturbance of the field, as it is also called, can be seen in the next video. So what you will see in this video is the result of that moving charge generating an electromagnetic wave. It will be a spherical wave, and this simple blue line here in the animation should represent simply the border of vacuum to some matter. So below that blue line you find matter, above that line we have vacuum. Now let's start to see what happens if the moving charge generates an electric field. So this moving charge generates an electromagnetic wave, seen here in the violet wavefronts. And what you also see is the horizontal straight line representing an interface to matter. So watch this, and now you see the reflected parts as well. They are very light in color, but you can see the reflected parts of the wave and the transmitted part of the wave, and that is the change which is applied to the electromagnetic field by the presence of matter, and that leads to the simple well-known macroscopic characteristics of reflection, transmission, diffraction of light in matter. After this rather complex general equation, we now shall look at some simplified examples. The first simplification is we take the matter out. So we consider the inhomogeneous general wave equation without matter in pure vacuum. What you see here is the assumption and the consequence of this assumption that we have no polarization, meaning that we have no bound charges, and we have no current density, meaning we have no moving charges, so there's no matter. And then the wave equation simplifies to this expression here, where now simply the second derivative to the space is correlated to the second derivative of the time. And the constants of proportionality is just the speed of light square, which relates to other electromagnetic constants like the permittivity and the permeability. If we separate the solutions and take the ansatz of an exponential time dependence of the electric field, we end up with an expression just for the spatial behavior, of course with the corresponding time dependence which is set in the ansatz, but that basically then gives us what we call the Helmholtz equation, which is maybe the wave equation that is familiar to you already. And that again correlates the second derivative of the electric field in space simply with the field magnitude itself. Proportionality factor is the wave number k, which is correlated to the frequency of the light just in the matter shown here. Another example are spherical waves, and if we put in a solution which is proportional to a radius, then we get the simple equation as a solution for the spherical waves. Again, you see the time-dependent part of the solution with exponential I omega t, and the spatial part simply is IKR, where R is the radius of the electromagnetic wave. Next example, similar simple to the spherical case, is the plane wave, in which now we take an ansatz where the solution again is proportional to the exponential dependence in time, and then the solution of the corresponding Helmholtz equation gives us the simple plane wave expression k times x, where k again is the wave number, and you see the plot on the right hand side that those are linear wave fronts which then move in the direction of k. So up to now this all was very mathematically, and we could ask the question, how do these electromagnetic waves look like? I mean, what is the physical nature of the electric field, the magnetic induction, and how are they related? And this can be derived fairly simple by inserting the solution of the wave equation into the Maxwell equations. So in doing so, we take Gauss' law, and if we look at Gauss' law in vacuum, then it reads that simply the divergence of the electric field equals 0. And now if we look at the solution for plane waves in this context, the result is that the product of the wave vector and the electric field equals 0, because this is simply the application of the space derivative, and we end up with k times E, and this has to be 0, which means that the electric field is always perpendicular to the wave vector. And for the magnetic part in an analogy, we take Faraday's law of induction and see what happens if we perform the derivatives. Then we get IK times the electric field is proportional or equal to time derivative of the magnetic induction. Or if we integrate that, we get the expression that the magnetic induction is proportional to the electric field and the wave vector k linked by a cross product. And that means that B, the magnetic induction, is always perpendicular to E and to K, which again, as we saw above here, are perpendicular. If we look at this in a sketch, in a schematic drawing, then we see that the electric field is always perpendicular to the magnetic induction, or in vacuum, the magnetic field. So those two are always perpendicular, and they both are perpendicular to the direction of propagation, which is defined and given by the wave vector k. So we learned a lot about the wave equation, its origin in terms of the Maxwell equations, and saw some special cases of application like plane waves and spherical waves. And those solutions can be used wonderfully to describe relevant phenomena in lasers and laser applications. Let me give you two examples as an outlook. Number one is the Gaussian beam itself, which you see a plot here in a simulation. And you already can see that in the center of a focus, we have more or less plane behavior of the wave fronts. So this can be described by plane waves. And as soon as we have divergence and significant divergence of the beam, there will be a combination with spherical waves. So this will be very useful to have these simplified solutions of the wave equation. A second application of such wave solutions is Kirchhoff's diffraction formula, where we use a huge number of spherical waves and analyze their contribution by summing up this contribution and achieving a new distribution of the field, the diffracted wave at an aperture, as an example.